Good morning everyone. Myself N.Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering. So in the previous modules, we have seen Unit 1, which are nothing but plates subjected to bending, twisting, transverse load, combined bending and in-plane loading, and followed by the energy method. Now, in this module, we are going to start Unit 2, and which is the buckling of thin plates and unsymmetrical bending. So in the starting of this module, and we are going to have a session today on buckling of thin plates. Now, so previously in the mechanics of solid subject, and we have a term called bending. So whenever you see this bending, shear force and bending moment, and we used to draw shear force diagrams, and we used to draw bending moment diagrams. So basically, let us have a small example on, for example, a cantilever beam when we have like this, and in this cantilever beam, and we need to draw the shear force and bending moment diagram. Now how we are going to get shear force or bending moment diagram? So let us assume a load P which is acting at the free end of the cantilever beam, and let us assume the length as L. And now when it comes to the force, now this is the only force that is acting on the beam, which is nothing but at the free end, and now this can be considered as shear force. And since the only force that is acting at the free end, the same force will be carried forward till the fixed end. Now we write shear force, and usually how do we write? We'll take a section at a distance of x from either free end or fixed end, and then we try to write shear force at any section x, and then followed by the bending moment. Now when it comes to the bending moment, now bending moment, we know that bending moment is nothing but force into perpendicular distance from the point where we are calculating the moment. And therefore, if you try to write bending moment at this section x, then we write mx as bending moment, and which is nothing but force into perpendicular distance. So force is P, and the perpendicular distance from the point, this point to the section, that is nothing but A, and again it is going to give sagging moment, hogging moment. So therefore we are going to get negative sign, so minus P into x. Now this is the bending moment. So bending moment deals with the forces which is acting transverse to the axis of the beam, and then followed by the perpendicular distance. Now here, when it comes to this topic, buckling of thin plates, so again in the previous classes we have seen what is buckling. Now let us define buckling. So buckling is nothing but it is a phenomena in which the material or the beam or the column, so they undergo different types of loading, and as the loading is gradually increasing, and you can able to see the deflection in the material, and therefore if you try to increase the load, then it's going to deform further, and whenever the ultimate compressive load in that is reached, then the material will buckle. That means it is nothing but a instability condition that occurs in either beam or column or any material. So unlike the bending, so bending is nothing but that is whenever we apply the load, the beam bends about an axis through a perpendicular distance, and whereas buckling is nothing but the instability phenomena that occurs in either columns or beams or plates or any other material when the load is gradually increased. So this is a clear understanding we should have between the bending and buckling. Now let us come to this buckling of thin plates. Now thin plate we have seen in the unit 1, and in thin plate in which we consider two dimensions, A cross B, and then followed by we consider thickness, which is very small when you compare with the lateral dimensions. So before this buckling of thin plates, let us try to remember the other one, that is buckling of columns. In the previous subject, that is Aerospace Structures 1, and we have a topic called buckling of columns. So if you try to look at this phenomena, buckling of columns, so let us try to draw a column, okay, and let us assume the end conditions of the column are hinged or pin jointed, and let us try to apply axial compressive load of P. Now, whenever you apply this load, the the column is going to deflect, and then you're going to get the final deflection shape like this. Okay. And then you can consider nothing but what? Whenever the critical load, that is P critical, whenever the critical load or buckling load is reached in this material, then it will buckle. And the formula for this critical load, P critical, is given by pi square EI by L equivalent square, where E is the Young's modulus, I is the moment of inertia, L is nothing but the length of, L equivalent is nothing but the equivalent length of the column. So this equivalent length of the column, it changes according to the end conditions. For example, for this column, we consider both the ends are hinged, and next other condition may be both the ends are fixed, and the other condition may be one end is fixed, other end is hinged, and the other condition will be one end is fixed and other end is free. Now, when both the ends are hinged, we can assume that equivalent length is equals to L, and when both the ends are fixed, then its equivalent length is 2L, and when one end is fixed, other end is hinged, you can consider the equivalent length as L by root 2, and when one end is fixed, other end is free, you can consider the equivalent length is 2L. So, by substituting these equivalent lengths for the different end conditions, we can substitute in place of here, and we can get the critical load for any of the different types of end conditions for a column. So, this is the phenomena in which we calculate buckling load of a column. Okay, and so now we are going to extend. We know that the column is one dimensional, and we are going to extend it for the two dimensional. Now we are going to extend it for the thin plate. Similar procedure may be adopted. In this case, we consider the column as one dimensional member, one structural member, and then we'll consider the next one as thin plate, in which this is the two dimensional member, and in which it has A cross B as the dimensions, A cross B, and we assume the thickness is very small when we compare with the thin plate. So, like this, we are going to extend the concept of buckling of columns to the thin plates, and then we'll going to have a session on this one, buckling of thin plates. Now, so let us go into this topic. The learning outcomes in this module are, we are going to able to differentiate between the bending as well as the buckling, and we are going to analyze the buckling of thin plates as well. Now, buckling of thin plates. So, thin plates, we know that they are relatively small, and the compressive loads which are acting on the thin plate, which are prone to buckle, and therefore they must be stiffened along its edges. Okay, so a thin plate in its general configuration, it has 4 edges. So how you are going to stiffen the thin plate so that the buckling can be delayed? So as we discussed, buckling is an instability phenomena, and then therefore when you try to add the loads, it's going to lead for a buckling phenomena. So therefore you need to delay the buckling so that you can add stiffeners so that the buckling will be delayed. So, and what happens when the stiffeners are attached? So a normal thin plate, when you have like this, and when thin plate is there, for example, if you look at this diagram, so this is a normal thin plate, and for example, if you try to attach any stiffeners to it, and here any, and on the 4 edges, let us assume on the 4 edges, if you try to take, stiffeners are attached. So what happens? The load carrying capacity of the thin plate increases. So therefore, and before the thin plate buckle, the stiffeners will buckle. Okay, so the stiffeners, when it's add to the thin plate, it's going to take more and more load than the normal thin plate without stiffeners. So because of this, the stiffeners, which will have very less in weight, they are attached to the thin plate, they are able to carry more number of loads so that the buckling phenomena can be delayed. So the stiffeners which buckle before the plate, and it depends on their geometry. So they may buckle as a column. Just now we have seen the example of a column, and which we'll call it as column buckling, and they may buckle like a plate. Okay, So buckling loads are much lower than those likely to cause failure in the material of the plate. So buckling loads are much lower than the normal thin plates. So a thin plate may buckle in the variety of modes. So it depends on different conditions, like it may depend on its dimensions, or like A cross B we consider, or it may depend on the loading what we consider, or it may depend on the method of support. Just now we have seen the method of supports. So the end supports may be hinged or pin jointed, or it may be fixed, or it may be fixed and hinged, or it may be fixed and free. Okay, so based on this method of support, loading, dimensions, so the thin plate may buckle in the variety of modes that can be possible. So in this diagram, we are able to see a thin plate, and in which NX compressive load is acting. Again, you can see the cross section of this beam, that is dimensions of the beam, that is A cross B, and in which X, Y, Z axis system has been taken, and X axis is taken in this direction, Y axis is taken in this direction, and Z axis is taken in this direction, and NX per unit length compressive loads are acting on the two edges of a thin plate. So therefore what happens, so this is just like example. Now if you try to discuss it with a column, so you can consider this as a column, and then in which the compressive load that are acting over here, and then when the compressive load is increased, so it's going to deflect, and this column is going to buckle like this, is going to deflect like this. So similar fashion, the thin plate also may try to bend or deflect in this manner. So this is the maximum deflection it takes before the failure occurs in the material. So whatever the amount of load it takes, the before failure cannot occur, it is called as a buckling load. So this is for example, this is a maximum deflection. You can consider it as Y max. So this is the maximum deflection, and therefore, so because whenever we get the maximum deflection, the plate will buckle or fail. Okay, so the buckling is nothing but the failure in the material initiates. Still, if you try to increase the load further, then it's going to take more and more to the failure condition. So because of this, so just before the failure occurs in the material, whatever the amount of maximum load it takes, then it is called as a buckling load. Now in this we are going to determine the buckling load for the thin plate. So the simplest form of the buckling arises when compressive loads are applied to the simply supported edges and the unloaded edges are taken as free. So that is what we have seen here. So on the two edges, it is taken simply supported edges, and other two edges we consider it as free. So it is a 2 SS and 2 free condition, 2 simply supported edges and 2 free edges. Okay, so in this way, so this is a simple configuration what we consider to understand and to calculate the critical load for the buckling, critical load for the thin plate. So a thin plate in this configuration behaves in exactly same way as a pin-ended column, so that the critical load is predicted that by Euler theory. So earlier we have discussed, that is column with different end conditions and the equivalent lengths also we have seen, and then we have seen how to calculate the critical load, that the formula we written, that is pi square EI divided by L equivalent square, that we have seen. Okay, so this is a critical load formula. Critical load or buckling load or crippling load all are the same. So this is a critical load for the column. Okay, so whatever the thin plate we considered here, so it exactly behaves like a thin plate, and its critical load is given by a Euler theory. So the formula what we written here is been predicted from the Euler's theory for long columns. Okay, so as we know that once the critical load is reached, the plate is incapable of supporting any further load, and therefore the buckling for such plates takes the form of bulging displacement of the central region of the plate, while the parts adjacent to it, the supported edges, remain straight. So what happens when the buckling of such plate occurs? So you are going to find the changes in the dimensions of the plate, and you can slightly see the bulging of the displacement from the central region of the plate. Okay, and while the parts adjacent to the supported edges, and we have seen two edges are simply supported and two edges are free. So remaining edges they remain straight, but the loading edges what we see, so they suffer some kind of displacement whenever the buckling occurs. So these parts and whatever the remain straight, so these parts enable the plate to resist higher loads, so which is an important factor in the aircraft design. So whatever the parts that we are seeing, parts adjacent to the supported edges remain straight, so these other edges they try to carry more and more loads, and which is an important factor in the aircraft design. Now let us consider the deflected shape may be represented by an infinite double trigonometrical series as W equals to summation m equals to 1 to infinity summation n equals to 1 to infinity amn sin m pi x by a sin n pi y by b. So this is a similar deflection function we have assumed even for the unit 1 also. So here also we are going to assume the same one, and then we are going to write the total potential energy. The total potential energy we have seen in the unit 1, that is, it is the summation of strain energy stored plus the potential energy of the applied loading, that is U plus V, and we have seen the formula also in the previous session, that is U plus V, that is equals to 1 by 2 integral 0 to A integral 0 to B into D into dou square W by dou X square plus dou square W by dou Y square whole square minus 2 into 1 minus nu into dou square W by dou X square into dou square W by dou Y square minus dou square W by dou X dou Y whole square, and then we are going to add this V also, and V, that is the potential energy, since in this diagram we consider the Nx compressive load, so the potential energy due to the Nx compressive load is given by minus Nx of dou W by dou X whole square into dx dy. So earlier we have seen the potential energy, that is V equals to 1 by 2 minus 1 by 2 integral 0 to A integral 0 to B, and then we have seen Nx into dou W by dou X whole square plus Ny into dou W by dou Y whole square plus 2 Nxy into dou W by dou X into dou W by dou Y into dx dy. So we have seen this formula, so which is nothing but the potential energy of the in-plane loads. Okay, but in the diagram what we considered here, we just consider only Nx compressive load. So in this case you can assume that Ny equal to 0, and also you can assume Nxy equal to 0. So Ny equal to 0 as well as Nxy equal to 0, and then when you substitute in this equation, so this Ny corresponding term goes to 0 and Nxy term corresponding to this goes to 0, and you left with only this one, and that has been added to the strain energy U over here and written as a complete equation, that is U plus V. Okay, so now what we are going to do here, even this also we have done in the previous session, that W is nothing but the deflection function what we assumed, and if you look at it in the equation, complete equation, so W should be differentiated twice with respect to X and to be substituted here, and again W, this you can assume this as equation 1, and it's equation 1 again, it should be differentiated with respect to Y and twice and substitute over here. Similarly substitute here, here, and here W is to be differentiated with respect to X once and then with respect to Y once and substitute here, and then it will be squared, and again here it is a simple differentiation, that is differentiating one time with respect to X. So differentiating W with respect to X and substitute here. So when you substitute all here, for example, if you try to look at it here, W, and when you try to differentiate with respect to X, let's assume dou W by dou X, then what you are going to get, the Y term remains constant and X term, instead of sine it becomes cos, and then the coefficient of this X, which is nothing but what, m pi by a, so that we will write m pi by a. So this is one time differentiation. If you try to differentiate one more time, dou square W by dou X square, then what happens, this cos term, cos m pi x by a becomes minus sine m pi x by a and its internal differentiation is m pi by a, and then the sign term again y term remains constant, that is n pi y by b. Okay, so again, so if you, and there is another m pi by a from the first differentiation. So when you try to look at it here, dou square w by dou x square, when you do, you are going to get this m pi by a whole square. So that is what the result we need to take, m pi by a whole square, and sine is here you are getting sine m pi x by a, sine n pi y by b, which is similar like a w. Okay, so similarly you can consider again w, you can differentiate once with respect to y, dou w by dou y, and again whatever the result we are getting, you have to differentiate with respect to y and write it as the equation and substitute over here. Okay, so like that we have to do the normal differentiation of the w deflection function and then substitute accordingly in this complete equation, and when you do that, what you are going to get is this one. So u plus v, that is equals to pi power 4 ab by ab into d by 8 summation m equals to 1 to infinity, summation n equals to 1 to infinity, a square mn, m square by a square plus n square by b square minus pi square b by 8a into nx, summation n equals to 1 to infinity, summation n equals to 1 to infinity, m square into a square mn. So this is u plus v, and once we get this u plus v, that is the total potential energy, then what do we do is we differentiate this u plus v with respect to any unknown coefficient, and in this case the unknown coefficient is amn. So we differentiate u plus v with respect to amn and set the derivative equal to 0. And when you try to differentiate with respect to amn, as you can see here, here we have a square mn, it becomes 2 into amn, remaining all the terms you can write as it is, and then here also we have got a square mn, so here also you can write 2 into amn. So it is just like differentiation of x square, okay, with respect to x, that you are going to get 2x. So similarly differentiation of u plus v with respect to amn, and when you do with the amn, you are going to get 2 amn. So that is, these were the two changes that we are going to substitute here, and we'll try to reduce the form of the equation. So, and when the differentiation, when you are going to differentiate this and set the derivative equal to 0 for the minimum or maximum, so the load nx, now it becomes the critical load. So nx is the compressive load. Now when you try for the maximum condition, so it becomes the critical load. So in place of nx, we are going to substitute nx critical. Now our aim from this derivation is nothing but we are going to find out the critical load from the derivation. Okay, so and once you make equal to 0, and you can rewrite the equation, and nx critical load is equal to pi square a square d divided into 1 by m square into m square by a square plus n square by b square whole square. So this is the critical load formula for the thin plate. Further again it can be extended for with some other assumptions, and you can reduce the form of the critical load equation. So in the above equation, each term in the infinite series for the displacement corresponds as in the case of a column and to a different value of critical load, that is eigenvalue problem. So the lowest value of the critical load evolves from some critical combination of integers m and n. So as you can see, the m and n are any integers. So the lowest values if you take, and it gives a critical combination, and in this again if you try to assume n equals to 1, so which gives the minimum value, so that no matter what the values of m, a and b of the plate buckles into a half sine wave in the y direction, as so that we can get the critical load by substituting n equals to 1, and you are going to get pi square a square d 1 by m square into m square by a square plus 1 by b square whole square. And now we are going to consider this as one more thing, that is we are writing this equation as nx critical, that is equals to k into pi square into d by b square, where k is, we call it as buckling coefficient, and it is given by k equals to mb by a plus a by mb whole square. Okay, so now if you try to substitute this k over here, and you are going to get this equation again. Okay, so k is called as a buckling coefficient of the plate, and given by the minimum value of minimum value for a given value of A by B. So this A by B ratio also plays an important role because it is a ratio of the plate dimensions. So this buckling, now the K buckling coefficient, usually it is plotted as a function of A by B, that is K versus A by B, that is the plate dimension. Okay, so K is the buckling coefficient. Now this diagram will clearly explain you about the plot of K versus A by B. And if you want to determine the minimum value of K for a given value of A by B, so we plot K as a function of A by B for different values of M as shown by the dotted curves in the figure. So in this diagram, so K versus A by B has been plotted, and this curve, whatever you are seeing here, this is M equals to 1 curve, and this is M equals to 2 curve, and this is M equals to 3 curve, and this is M equals to 4 curve, and this is M equals to 5 curve. So the lowest envelopes are taken here, and the A by B values are also taken here. So here it is taken as 1, here it is taken as 2, this is 3, this is 4, this is 5, and then intermediate in between 1 and 2, there is root 2, root 6, root 12, and root 20, that is the A by B ratios, which gives the lower envelopes corresponding to the buckling coefficient, that is 4. Okay, so this we will see how we are going to get this root 2, root 6, root 20, right? So now as we can see here, and it can be seen that M varies with the ratio of A by B, and that the buckling load can be predicted for the minimum value of K, that is K equals to 4 at values of A by B, that is equals to 1, 2, 3, etc. Okay, so usually what we do is we'll first consider M equals to 1 mode, and then we'll consider M equals to 2 mode, and then we consider M equals to 3 mode, and so on. So in general, if you want to generalize this, so you can consider this, you are writing K value for M mode and then M plus 1 mode. So if you take M equals to 1, and here it becomes 1, here it becomes 2, if here it becomes 2, and here it becomes 3. So that is in general. So what we are doing here, it is from the formula of buckling coefficient, that is K equals to MB by A and A by MB, and then we are going to write this next mode, that is in place of M we are substituting M plus 1, and here also in place of M we are substituting M plus 1, and we are trying to get a relationship between A by B ratio and M, so that we are going to get A by B equals to square root of M into M plus 1. Okay, so now here if you try to substitute M equals to 1 here, and when you substitute M equals to 1 in this equation, and you are going to get A by B ratio equals to root 2. So 1 into 1 plus 1, that is root 2. If you try to substitute M equals to 2 here, you are going to get A by B ratio, that is 2 into 2 plus 1. So that is nothing but root 6 you are going to get. Similarly, if you try to substitute M equals to 3, you are going to get A by B ratio as root 12, and so on. So these are the lower envelopes that we have seen in the diagram here, that A by B ratio is root 2, root 6, root 12, root 20, and so on. So it depends on the substitution of M equals to 1 for the A by B ratio. So that we got these values. Okay, so now here, so you got these values, and then finally if you want to calculate the critical stress, and you can write the critical stress as Nx critical by thickness, and therefore the critical thickness, the critical stress, that is given by K pi square E divided by 12 into 1 minus nu square into T by B whole square. Okay, so Nx critical formula we have seen in the previous slide, that is Nx critical, that is equals to K pi square D by B square, and you can substitute for K, and then D, which D is nothing but the flexural rigidity, which is the product of E and I. You can substitute moment of inertia of the plate, and therefore when you substitute all these things, you are going to get the critical stress, that is K pi square E divided by 12 into 1 minus nu square into T by B whole square. So this is also called as buckling stress, critical stress, or buckling stress, okay, or the crippling stress. Okay, so this is the buckling load. Now till now we have seen the elastic buckling of the plates, and in this slide we are seeing inelastic buckling of the plates. So whenever the inelastic buckling of the plates that are there, and we got in the similar formula, we are going to add neta factor, and where neta is given by the experimental evidence, that is equal to 1 minus nu e square into es by 1 minus nu p square into e into 1 by 2 plus 1 by 2 of 1 by 4 plus 3 by 4 into et by es whole to the power of 1 by 2, where here we know that nu e and nu p are the Poisson's ratios in the elastic and plastic zones, and es and et are nothing but the secant modulus and tangent modulus for any particular plate. Okay, so this we got from the experimental evidence. So for the case when the elastic buckling is there, so for plates having the lowest values of b by t, so the critical stress may exceed the elastic limit of the material of the plate, so that the capital E Young's modulus become dependent on stress, as does the Poisson's ratio also. So all these changes are usually included in a plasticity correction factor, that is neta, and the neta formula is given by this. Okay, so that's it for the today's session, and we are going to continue in the next module. So in this module we have seen the elastic buckling of the plates and inelastic buckling of the plates. Okay, so in the next module we are going to see the experimental determination of critical plate. Thank you.